So the last speaker of the intelligence track for this conference is Kevin Ellis, a student in Josh Tenenbaum's lab, who's going to be talking about DreamCoder and probabilistic program learning. Sorry. Probabilistic learning of programs.
Hi, I'm Kevin Ellis. I'm going to be talking about joint work with Lucas and Matthias Sablemeyer, who were students in Josh's lab as well. I'm in Josh's lab, and this was advised by him and also Armando Solalezama. So you can think of lots of different kinds of human learning and inference and construction as being different kinds of program synthesis. So human software engineers write lots of code, but you can also think of, for example, language acquisition as a kind of programming. Like we learn programs for making syntax trees, we learn logical forms or denotations for representing the meaning of utterances, and we learn motor programs for producing speech. If you look at the kinds of artifacts that humans produce, you also see a lot of program-like structure. You see symmetry and repetition in the arch. You see the compositional reuse of arches within the Roman aqueducts. There's programs everywhere. And it's the same story if you look at the kinds of artwork or the kinds of technical diagrams that we produce. You see this compositional reuse of combinatorial structure. So this is an old idea. It goes back all the way to Solomonov and Fodor, and it's come up in lots of different forms. But I think that one of the nicest modern realizations of this idea is this work by Brendan Lake, which was published in Science a few years ago, and a lot of you have probably heard about it. Some speakers here brought it up as well. So what Brendan Lake did is he built a really sophisticated model which could look at an image and then infer a probabilistic program for generating that image. And he showed that you could account for a lot of the human understanding and recognition and generation of handwritten characters through a kind of probabilistic program synthesis. So I think that the challenge now for AI is to build systems that are kind of like Brendan's, but instead of being engineered for one specific class of problems, they can be exposed to a new class of problems and then learn or grow into being domain experts at that particular kind of program learning. So I'm very inspired by this kind of work and closely allied directions of research. And I think that now what we need to do is we need to build a system which can grow into a competent program learner. So if you look at these kinds of systems, their success typically hinges on two key ingredients. So one of those ingredients is a domain-specific language. It's like a generative model over programs. It's like a library of concepts or a library of code. It tells you, it narrowly scopes the kinds of programs that you ought to be considering. The second key ingredient is an inference strategy. It's some kind of procedure for looking at a handwritten character or looking at a curve or some input outputs and saying, oh, these are the kinds of concepts, the kind of code that you ought to use to solve that kind of problem. So in old school AI terms, it's kind of like declarative and procedural knowledge. And you need both of these ingredients in order to get program learning off the ground in a new domain of problems. So as a concrete example of the kinds of problems we'll be looking at, a really simple instance are these symbolic regression type problems where you might see a curve and have to spit out a function that plots points along that curve. So the concepts would be things like polynomials, squaring, rational functions. Or you could look at graphics programs where you see an image and you need to write a program that draws that picture. So here the concepts that we need to learn are things like circles. Maybe circles aren't built in. Maybe we don't know when to draw circles or where to draw them. And we need to infer both of those things. So just to flesh out this idea of a DSL or a library of concepts a bit more, you can think, so in the programming languages community, people often build these things called DSLs, which are libraries of code which tell you for a specific domain how to write programs, like what are the program pieces. So here I've drawn 3 different programming tasks on the left-hand side. If you look at the upper left-hand task and think about it for a bit, what you'll see is that you're taking a list of numbers and then only taking the numbers which are at least 2. You're removing all the other ones. And that's a really simple program if in your DSL you have a procedure for filtering out things from lists. And I've labeled that as F1 here. And if you look at the DSL column, you'll see a chunk of code labeled F1, which is a higher order function for filtering things out of lists. So the challenge is going to be to look at a bunch of tasks like this and write the programs that solve those tasks. And at the same time, we want to infer this DSL, this library of concepts. So we have a new algorithm for doing this, and it's called DreamCoder. And the reason why we call it DreamCoder is because it's based on a kind of wake-sleep learning. So it has a wake phase where it uses its current DSL as well as an inference network, like the kind that Frank Wood was talking about earlier, to search for programs that solve the task. And then it has a pair of sleep phases, one where it grows or improves its DSL, its generative model over programs, and another where it trains an inference network, which here I'm going to call a recognition model. So we're going to apply DreamCoder to a few different classes of problems. In one kind of problem, we're going to be looking at writing Lisp code for manipulating sequences. Another kind of problem are these symbolic regression type tasks, and we're also going to infer graphics programs. So this was heavily inspired by another algorithm called exploration compression, created by A.L. Dechter, who was a grad student in Josh's lab. So first I'm going to talk about the exploration compression algorithm's analog of the wake phase. So in exploration compression, the setup is you have a DSL, or a library of concepts or code, and from that you draw a whole bunch of programs, and then those programs are executed to produce images or curves or input outputs, and your job is to work backwards both to the programs and to the DSL. A new twist we're going to add here is we're going to have an inference network, and we're going to train it to look at some data, so like input-output examples or an image, and work backwards to the program. So this is a kind of amortized inference. So the way that wake worked in the exploration compression algorithm is you took your current DSL and you just enumerated programs in order of their size, and you saw whether any of those programs solve the tasks that you needed to solve. So here you maybe have some sequence transformation tasks, you enumerate some programs, and you store the solutions that you got for those tasks. What we're going to add here is an inference network, this recognition model, which is going to be a neural network that looks at a task and then biases the search. The way that it biases the search is kind of like the DeepCoder system, if you're familiar with that. But at a high level, what it's doing is it's predicting a distribution over programs conditioned on what that program needs to do. So we're going to use our neural network coupled with the DSL to search for solutions to the tasks that we need to solve. So we get all of these solutions, and now we want to update our generative model, our DSL. So we go through our first sleep phase, and what we do is we replay the experiences we had during waking, and we search for common pieces of code and abstract them out or compress them out. It's a kind of refactoring, and we use this to update our DSL. This refactoring is guided by a minimum description length or Bayesian objective. Then we have a second sleep phase whose job it is to train the recognition model, and we train it on two sources of data. So the first source of data is the programs that we found during waking. So if we found that this program solves this task, we train our neural network to say, when you look at this task, predict this program, or predict a program that looks like it. The problem with this experience replay, though, is that we're considering a regime where we only have maybe 100 tasks to solve, right? Like you should be able to become a competent programmer after looking at maybe a few hundred problems, not a few 100 million problems. So we can augment our data by dreaming or sampling during the sleep phase. So we can just take our DSL and imagine new programs, run them to see what they do, and then train the network to predict the hallucinated program when it sees the hallucinated data. So as a first example of something that we've applied this algorithm to, a master's student in the lab, Lucas Morales, created a really nice data set of 200 functions on lists. Here are a few example functions, and if you throw this algorithm at Lucas's corpus of problems, it discovers a network of 38 different subroutines, most of which are fairly interpretable. I think the most interesting thing it discovers is this higher order function, or filter function, and the reason why it's interesting is because you really need programs as a representation in order to be able to even represent something like filter. So you can play the same sort of game, but not with lists of numbers, but with lists of characters. So these are text editing problems. And what you see is that prior to learning, the system is really, really terrible at these problems. It solves 3% of them. This is on a standard corpus of text editing program synthesis problems. And then after about 3 wake-sleep cycles, it works its way up to solving most of the problems. So if you look at the actual learning trajectory, it sort of starts low and then climbs and then levels off. So what's happening here, the reason why it starts so low and then like inches its way up is because over successive cycles, it's accumulating this network of subroutines, these new DSL primitives that's learned during the sleep phase, and then building on them. It's like growing a library of routines or concepts. If you actually look at the routines that are learned in successive iterations, they look like this. This is written in lambda calculus. It's impossible to understand. But if you draw on top of it what each of these functions do, it becomes much more understandable. So here I've drawn 3 columns of subroutines showing the functions that were learned on 3 sleep cycles. So on the final sleep cycle, it learned how to surround text in parentheses, which builds on string concatenation. That makes a lot of sense. Or it learned how to abbreviate a sequence of words, the first letters of words down there in the bottom, which relies upon being able to drop characters from sequences. So if you look at this mess of lambda calculus, you'll see things like map and fold, and that's because I just gave it map and fold for free. It didn't have to learn those things. So there's no sense in which it was learning from scratch. It's not really clear to me you want to learn from scratch. I think the goal is to learn in a way which is domain general. But in principle, with enough compute and with the right spectrum of tasks, you ought to be able to learn starting from something like a minimal Turing complete basis. So as a basic sanity check to make sure that actually happens, what we did is we took a minimal subset of primitives in 1959 Lisp, and then we gave it like a problem set of 22 functional programming exercises. And then we ran this thing for about 100 hours on 64 CPUs. But the results were, I liked them because the first thing it discovered was fold, and then it discovered like unfold, and then it used the fold it had discovered to define map. So here it recovered a lot of the primitives that previously I had to bake in. So I think it's a sanity check. I'm not suggesting you should actually ever do this. I think you should build in, you should not start from a minimal basis with just like cons, car, coulter, and the Y Combinator. You should build in things which you know are generically useful. Like as programmers, we start out with like Python. We don't start out with Turing machines, right? You don't actually want to do this. This is just a sanity check. So we applied this to some symbolic regression problems from images, but I think that a more interesting image domain is this domain that was built by Matthias Sablemeyer, who was a visiting student in the lab at the time. So he built a world with an agent that controls a pen, and the agent can move the pen forward, which draws a line. It can rotate the pen, which draws angles. It also has a looping primitive, so you can draw like regular polygons and things like that. It can pick up the pen and put the pen down, and you can make all sorts of different kinds of pictures like circles and spirals. And he made a collection of around 100 different drawings, and then we gave these drawings to the system and said, find programs that make these pictures. And the DSL that it assembled had different geometric drawing primitives that it did not start out with. So for example, it learned to draw circles, which make a lot of sense. You saw a lot of circles in his training corpus. And then it also learned parametric drawing primitives. So for instance, it learned this square drawing primitive. This is the same DSL primitive that it learned being run with different arguments, and it draws squares of different sizes, or things like stars or spirals. Some of them look more like parametric arcs. If you look at the dreams prior to learning, they look very uninteresting. They're kind of like lines with the occasional loopy looking thing. And then after learning, what you see is kind of like a remix of the stuff in the training data. So it learned a DSL, which had things like squares and triangles and regular polygons. And then when it dreams, it imagines new scenes that compose those pieces in different ways. And that allows it to train a neural network on a lot of data, even though it was only given a small collection of drawings. So here's an example of one of the dreams. I'm drawing in dark color where it started drawing, and then in light color where it ended drawing. So it's kind of composing the circles with the spiral. This is another highly regular one. There were a lot of squares. It composes them into grids sometimes during its dreams. This one's highly regular. Some of them look more like squashed bugs. It's more like the texture that you get from this. You don't really get a whole lot of high-level geometric structure. Here's another example of a dream which doesn't have a whole lot of high-level structure. So taking a step back here, the reason why we want to do this is because it's not because we want to solve software engineering problems. We're not trying to like write the kind of code that software engineers write. We're trying to write the kind of code that we think our head might be writing something like when we're learning to solve a new class of problems. And this means two things. This means learning the vocabulary of the domain of problems, and it also means learning how to deploy that vocabulary effectively. And you can think of this as like a domain-specific language and an inference network or a recognition model. So that's it. Thank you. I'll take questions.
something about when you're training this network, what's the loss function between the graphics image and the generated programming graphics image? How are you, I'm missing something about how the adaptations happen.
Right, so we measure the pixel-wise distance, and if it's close, then we say that it was a perfect match, and if it's far apart, then we say it was a total mismatch. You
so
could
in
just
that case, you have no gradient information to get close.
Right,
So
yeah.
Dream up something else. So you're relying on the fact that you'll eventually find something that's close for each problem.
Right,
Okay,
yeah.
Great.
Thanks for the talk. I think it's a very creative approach. Have you thought about how to apply this type of probabilistic learning to learning probabilistic programs?
Yes. So I think it's doable. We're trying to do it with probabilistic programs that generate text, so like probabilistic regular expressions. I think the challenge is figuring out when a program is, because with a probabilistic program, you don't have this like all or nothing feedback. So you don't really know when you've solved a task. And that makes things a bit tricky, and we're still trying to figure out how to make that work. But it's a good thing to work on and think about.
Have you thought about combining this with some form of curriculum learning where you expose kind of I guess the agents to increasingly complex problems?
Yeah, so Matthias actually experimented a lot with that. And in these particular experimental results, that wasn't using curriculum learning, but I know that he got some mileage out of that. I don't recall exactly how big the gap was.
Can you talk a little bit about the robustness of the examples that we're seeing?
So like, you know, if I were to replicate the learning procedure for about the amount of time that we use, maybe what fraction of the time do I see concepts that make as much sense as the ones you showed?
The concept, it's usually pretty reliable in learning like human interpretable concepts. I think that a lot of that has to do with the fact that our program representation looks like Lisp. So in a much earlier generation of a system like this used combinatorial logic, and sometimes those concepts looked a lot harder to understand. I think you get a lot of mileage out of using something like Lisp. Thanks.